Morning to you all, and we are starting our third day. So, I know, like this, we completing 5 days, and you will see like every day is a new things. But so far, I think what I feel is very good. I see a lot of interest and on all those things, and I think we should keep it up so that our main goal will fulfill. So, yes, we will discuss about the seismic design. Like what? Basically, we are mostly covering the basic things, like what everybody should know that. But the seismic is a more complex than what we showed for our stability analysis. It's a very simple method. And if you see the time it takes, for example, when we do a limit equilibrium model, hardly 1 to 2 weeks. And if we do a static stress deformation model, we go like 4 to 5 weeks in the modeling. But when we do this dynamic model, it takes like 8 to 9 weeks because of again in the numerical, the advantage of numerical model, you can simulate. We simulate a lot of behavior, so you can change properties and run again, change properties and run again. But in the and dynamic model, each run may take 2 to 3 days. So that's why it's very complex, and people are there, like experts are there, they mostly do the dynamic deformation analysis. They mostly focus on that, but we will touch what are the basic things we do for the dynamic. So first of all, we have to have a dam classification. Why this is important? This is one of the classification by Canadian Dam Authority, CDA. And but in every country or state they have their own, but it is similar kind of classification. So we see that we said it is a very low level. This is the level, like where we are. It's a low means there is no risk and there is no loss of life. That means if it fails, this classification based on if during a seismic event the dam fails, and low economic losses, and it contains very limited infrastructure or services. So if during the seismic event we are not seeing much effect. Then the significant, but it's a temporary one. And again, the loss of life is very difficult to determine. No significant loss, marginal loss of marginal habitat only, and restoration will be possible. Like after the loss, we can again do some restoration work, we can bring it normal very quickly. Losses to our recreational facilities, workplaces, and infrequently used transportation routes. So those transportation routes are also not vital. So that's why this is called significant. Then we go high. In the classification it goes high, which is permanent. Means once it is gone, means it is all gone. And loss of that, these numbers are also very important because that depends on the population affected by the damage during earthquake. So 10 or fewer, significant loss, and but still restoration is possible. High economic losses, again loss to the public transportation and commercial facility. Then very high, 100 This number goes to 100, from 10 to go to 100. Again, significant loss. Restoration is not possible here in case of high classification. Very high economic loss and affecting important infrastructure services like highway, your industrial facilities, storage facilities, and all those things. Then the extreme one, definitely extreme one is very much prone for the highly active seismic areas. There the loss will be again more than 100, and there will be major loss to the wildlife, restoration also impossible, extreme losses. So each site we will classify, and the next one I will show you why we will do the classification, because this is very important. In the modeling also you will see how the return, like annual exceedance of probability, like the return period we call it. So this is a 500-year event in case of low. Significant, we go to the 1000-year event. Next we go to 2500-year event. Next we go to 5000-year event, and the last one go to 10,000. Now most of the people even in GISTM, and they are saying that for tailings it will be always 10,000 years. You can see, like initially when we start doing the seismic modeling, so 5,000-year event was we are taking in the state of Arizona, where it is very low seismic areas. But now we are going to 10,000-year event. It's a conservative, but that's how we are designing. Because you can see that justification can be provided. If you are saying, then you have to prove that it's only very high. That any kind of classification you have to prove that, show the evidence. If you do not have evidence, that's in many cases. If you do not have evidence, you have to go 10,000. What we consider, again, I looked into, in India there is nothing like CDA, but I found that the Central Water Commission, they give guidelines. Again, yesterday also Professor Das was telling, in India there is nothing regulation, it's all guidelines. And again, these guidelines are for mostly for the hydro dams, but also the earth embankment, which tailings are coming under earth embankment. So anything they say, this is for earth embankment, the tailings will follow. So two important events we always consider. We call it OBE, operational basis earthquake, and MDE, the maximum design earthquake. What the difference? So one is during the operational time, because operational time is short. These things has to happen in our operation time maybe 20 years to 40 years. It has to happen only during that. So in that case, a big large event is not possible. Like probabilistically, when we do statistical analysis, that event, that's why we call that an operational basis. But I mentioned these tailings are not, the design is not over during the operational time, but after closure. So after closure, they are going for a long time. So they are always will have to consider the maximum design earthquake. So for the return period, operational design, their guideline says is between 144 years to 500 years. For 144 years for concrete dam and 500 years for embankment. But for the MDE, when you go for the maximum design earthquake, the return period, again they have a classification, low, moderate and high. But I was trying to see what is their classification, I couldn't find that. But again, you may look into the literature, there will be somewhere they say the high means like the CDA, high, moderate, low, they have some guidelines also for high, medium, moderate, low. So for high, 1,000, 3,000 and 10,000 years for concrete dam. That's why I didn't go much into what is high, moderate, low. Because when it comes to the embankment dam, it is 10,000 years. So they pretty much looks like took that guideline from CDA and then say that any embankment dam, it is now 10,000 years. It doesn't matter whether high or low. So we are like, if you take the guidelines, they are telling us we have to target these 10,000 events. First of all, we do, this is called seismic hazard analysis. In seismic hazard analysis, we have two types. One is probabilistic, another is deterministic. So I will just basic put what is a probabilistic versus deterministic. So we looked into several possible earthquake. For example, we are designing a dam in Canada, but there also we are looking into whatever possible earthquake is happening in everywhere. But there is some guideline, it should be happening within 200 miles, because that's how it can be affected if it is happening. But these people have become so conservative, like they are thinking, no, even if it happens somewhere else also, it happened, we can consider that it might happen here also. So there is a, like that statistical model, you have to develop a statistical model and do that. So this is also another analysis part before we go and do the dynamic model. So one example I am showing you. So we came up with the different return period. What is our PGA? Peak ground acceleration. That PGA is important. So like pseudostatic analysis, some you may be familiar with. In pseudostatic analysis, we use that PGA. So that's our horizontal acceleration. We use it when we do the limit equilibrium model and come up with the factor of safety. So like yesterday we were discussing, for static, if there is no earthquake, for static factor of safety is 1.5. But now we go and say if my PGA is 0.08 or 0.137 based on that. But again, here this one we stopped at 5,000 years because this is one example which we are doing before all these things developed. Like there is a big difference after Brumadinho 2020 when they came up with all these things and before. So before we are not going that high, like 10,000 was, we are not even considering, maximum we are doing 5,000, that's why I stop here. But again, we will have to also have, now in this seismic hazard analysis, we will develop that model. Again, this one is site specific. For each site it will be different. So one, that's why exactly latitude, longitude should be provided in the analysis. What is deterministic? So I always prefer the deterministic, because the deterministic is the important thing. So I will show you, the definition is the worst possible scenario among all possible seismic sources related to the study site. So that deterministic one, the engineer who is designing it or the engineer who is doing the seismic hazard analysis that will determine for that particular site. Like this is the model, that's the important. So again, the different steps are identify active faults, because we know like the seismic event is generated by a faulting. It's a tectonic process. So if you have active faults in your area, that's how we do study. In our study, we go and identify all the faults near the area, like in a 100-mile radius, we identify them, and then we do some further studies to identify which are active, which are inactive, and if active, and then we develop the model to find what will be this PGA if that fault along the fault plane the failure occurs. That's where we determine the maximum earthquake that could be generated by these faults. And again, there is attenuation laws, because that attenuation law is where the source, and then how far you are from the source. So definitely, as you go with the distance, this whole energy and that number will be reduced. Then we determine the hazard at the site. So there are two methods. The probability method, where even if you are, like I mentioned, even if you are in Canada, somewhere else in the world, that kind of big event occurred, that will be considered during the probabilistic. But in the deterministic, we are focusing which is likely to occur. So a lot of times, like people have less knowledge about the site, means the seismic activities of the sites, they go by the probabilistic method. But if we have expertise there, we can determine is yes, this will be the deterministic seismic hazard, then we go by that. Again, you can see how the PGA changes with the return period. So it increases like exponential. You go from 1000 to 10,000, this is like a logarithmic scale. It exponentially increasing. So it goes much higher. Again, we consider also same like in the static material parameters which are important. Here also we looked into, these are like the key parameters, and mostly this is the modulus G value. So those are again during the site characterization. We'll have to go through this, and then it will vary from site to site. This is just an example how a particular site we calculate these parameters. So for it can be starter dam, we can have a fine tailings, we can have a coarse tailings, we can have a different type of tailings. Then we go there and get those parameters. Time history. So the time history is important when we start the modeling, because what we do, we simulate these scenarios. What exactly the time history, we put that in the model, in our model, and do that. So this is the time history for the design earthquake. But if we are considering, this is for if we are considering the deterministic, we have a one model, we do that. But in case of probabilistic, we normally take like 2 or 3 design earthquakes, because each time the time history, you see the acceleration, how it is changing with time, and mostly duration is 20 seconds, maximum is 20 seconds. It's all happen during 20 seconds. So in that, sometime we see that is a very less, the PGA value is lower in that model, but it is continuing more than 20 seconds. So that's why 3 or 4 in the initial phase we go 3 or 4 and then identify this is our critical one. Then further development we do using that critical one.
Sir, what is the difference between horizontal time history and vertical time history?
How it is when like again we'll have to go back to the when the earthquake starts, its travels, its velocities or acceleration varies horizontally and vertically, both.
Okay.
There is horizontal variation and also vertical variations
Okay.
in the same wave which is coming. So both are important. This is called cyclic liquefaction. Like in earlier we saw how the static liquefaction occur, and the cyclic liquefaction is like you see the time history, it is going up and down, up and down, up and down. And this particular model is mostly coming from the lab. In the lab actually we simulate that. And we get most of these parameters are coming from the lab. The concept is the cyclic loading causes like the particles to rearrange, and that cause the increasing pore water pressure and decreasing the effective stress within the soil. So when you decrease the effective stress, simultaneously we see our shear stress is going down. If you see some of these earthquake areas, if you look at the data, you will be surprised to see there will be a rise of water level 100 feet during the earthquake. In the well where the groundwater is 100 feet below the surface, it can come to the surface also. So that's the power of that earthquake loading. In the earthquake loading, we have 2 important concepts. One is cyclic stress ratio, another is cyclic resistance ratio. I am just giving you the concepts. These are all covered in any soil mechanics books you go, you will find that, like how we can determine the cyclic stress ratio and how you can determine the cyclic resistance ratio. And then when we are saying the factor of safety for cyclic liquefaction, it is the ratio of CSR versus CRR. So one is a resisting force, another is a driving. And the liquefaction will start when CSR exceeds the CRR. Here you can see it starts with the stressed reversal, then it goes to the zero effective stress. Here you can see that shear stress and the shear strain, you go down to even the zero during the cyclic liquefaction, and then like that's how your stiffness is reduced. And then it says they are saying like 5% strain, when you cross 5% strain you start liquefying. And then these cycles, how many cycles is needed, all these things in the lab testing are very important here. I am not covering much into that because I am just giving you some basics. Yeah, this is one of the example which we also follow. Like there is another example also. We have like the M value. Based on the M value, most of the seismologists and also the seismic the engineers would model, because SPT value is the only parameter available. So based on the SPT data is also this, but mainly for the tailings, because I mentioned that in the tailings this SPT value is very confusing. It is very difficult to do that. So that's why we use this shear wave velocity. That's what we get from our CPT data. So we can see that this model was developed, it's a very recent model developed by Anderson Stoke, and the concept is like depending on the fine content, he developed with the shear velocity below which it can liquefy. If our velocity is less than that soil can liquefy, means during the cyclic liquefaction. And if it is higher than that, we are good, it will not liquefy. So this is again another guidelines you can follow. But again, we do the numerical model and see that whether it is liquefying or not. Just a typical cross section how these models are developed. You can see that it's a very complex model, and a small section you can see how many. This is a plaque finite difference model, and you look at the element size, and they should be very fine grids to get all the essence. That's why it takes so long to finish a model. So if you go back, like I showed you this number 8 zones are there, and pretty much in the same one we are coming up with this 8 model. And we can see that this is the water table. This is the water table assumed in the model. So above the water table and below the water table, they can be different material parameter. That's why it's called up the water table fine tailings, also up the water table coarse tailings. So same zone is a coarse zone, but it is if it is above the water table or below the water table. This is a very important concept. That's what we first check. And RU, I think we defined it yesterday, the pore pressure versus effective stress. That's the RU. And in the dynamic modeling also we see how the RU is varying, because when the pore pressure increases, your RU increases. And when it will liquefy, theoretically 100%. But always we do not go for 100%, because at 100% you have no control. So when we are controlling, we come up with like kind of 90%. If the RU value is 90%, then we see no, that's the dangerous trade that is coming. Here you can see we varied the PGA like with different, it can be OBE or MCE or MDE. So depending on we are going, like the 0.25 is 10,000 years. 0.085 is 1,000 year event. So you can see that RU is crossing that 90% when we are going to 0.2 G. So for that particular site, 0.2 G is critical. If you go beyond 0.2 G, then definitely there will be some trouble. So that's kind of the first screening we do, and then see like which one we will focus. So this is the result of the dynamic model. What we look into, what is the horizontal displacement? Because there is a criteria guideline which varies from site to site. That's why I am not showing that guideline. But here you can see that the maximum displacement is, these are in feet. These are in feet. So the maximum is in 10 feet. Here this model is showing with those things. If we apply 0.2 G, there will be a 10 feet of displacement. So then we have to see that if 10 feet is acceptable or not. So that is again the engineer who is modeling it, who is interpreting it, depending on the site, what is the site and is that acceptable or not. And you can see that here but why I am showing is like maximum we are seeing like a 10 feet. But when I go to 0.25, that 10 feet and this 10 feet only we are saying is happening along the slope in that a limited area. It is happening. But when we go to the PGA 0.25, we can see that whole dam is now, we are seeing like maximum is going like a 25 feet and now whole dam is above 10 feet, most of the things. So which is very clear, like 10 feet also a very big things. The guideline which is coming from the hydro dam and other important structure, we normally see should not be like we want to stay within 1 feet, acceptable. But again, it is not a standard, it's all depend on your area. But this is clearly showing me, like if I look into that, this model is clearly saying if this has liquefied. Definitely if it has gone like 25 feet, we are seeing this has liquefied. So seismic liquefaction is possible. So here I stop and any more discussion, like I want to put some discussion on the basics of these things.
So sir, you said that deterministic seismic hazard analysis and probabilistic seismic. So which one do you prefer? Like for
personally I prefer deterministic.
Okay, sir. So
but for
in general
deterministic,
practice, sir, people are using which model? Like which analysis? In general practice,
in general practice probabilistic.
probabilistic.
Probabilistic people are facing.
But sir, that will be uneconomical, no? Because in probabilistic, we are considering the earthquake happening very far distance from our location.
Yeah,
which
but
can
we are
be
conservative.
difficult.
People are like defensive is they are conservative.
And that design will be uneconomical.
Again, you like again what governs the seismic analysis? Like when we see something is happening, then we do the remedial measure. We can go back and do something and then come up with the proper design. Then we come up with, we change our design. We consider something different. This is like the initial case, we do that analysis and it is showing me definitely it will liquefy if you go to the 10,000. But the thing is, probabilistic analysis is showing that 10,000 event is possible. But the guidelines is already there, like you have to go for the 10,000 year return period. So that's why it's the probabilistic is also supporting that. You see, because it's already in the future it will be people are going into 10,000 year event for decades.
Sir, one more question. Sir, some areas are not into the earthquake zone.
Exactly.
Like in India, there are 4 zones, sir.
Mm-hmm.
The highest zone is the zone 4, which is considered occurred the highest earthquake magnitude, sir.
Yeah.
So if some, like my zone is zone 1, let us say, my area is in very less earthquake prone zone.
Mm-hmm.
Still, I have to design for the highest earthquake.
That's what this you see the CWC guideline is. Even if like I have thought with the agency and the people, like I have a lot of argument with them because I also come from an area like in Arizona, it's not seismically active.
Right, sir.
But they want to be defensive. They don't want to take the chance, like if, because you don't know. These are the earthquake, where it will occur and when it will occur and how big will be the size of the earthquake is completely unknown. There are faults also, we call them blind faults. They has not been yet discovered because this is all
the blind faults. After that, what did you say?
blind fault.
Yeah, that are
Blind fault is like the fault which has not yet been identified or discovered, but it can be possible.
Oh, even the less earthquake zone also there is a possibility.
There is a possibility. That's why
It can occur.
exactly. That's why if you see the deterministic, you should have more knowledge of the site. Adequate knowledge of the site you should have an expert there also who knows everything and can give the evidences that yes, I determine this will be the earthquake if occur in that. So there are a lot of site cases you may not find that. That's why it says if you do not have any evidence, then adopt 10,000 years. That's why the guideline is going towards that.
So if in that area, let us say in past 1,000 years back also there has not been any earthquake occurred. Still we have to go for the 10,000.
Again, the lowest one is 1,000 years. Everywhere we are adopting that. Even there is nothing. But again, depending on the site classification, if you are in the low zone or you are in the extreme zone, because the extreme zone is guideline go towards the 10,000 years. But if you are purely in the low zone, there the guidelines they are telling you go to the 1,000-year return period.
1,000 year return.
Yeah.
In 1,000 year also, if no earthquake has occurred in that area, then in that case.
No. That's the minimum you have to do. When you do the analysis, you have to consider that.
1,000. That earthquake has been occurred.
1,000 minimum was always we are doing. For any sites, when we are doing the pseudostatic analysis, we are considering always the 1,000 is minimum. Yes.
And so some of the areas, let us say if we are finding the type of material, clay type of material is there. So in that the chances of liquefaction are very low, sir.
Mm-hmm.
So still we have to consider this, as you mentioned that CSR and CRR.
That's where your lab data will be helpful. Because I mentioned you. In the lab also you can, in all this CSR and the CRR, you can determine that in the lab also.
Okay.
So in the lab they actually simulate the earthquake. That loading is generated in the lab and then they measure it. And from the lab data you can show the evidence, though my soil is good, nothing will happen there.
Yeah, especially in clay soil, sir, liquefaction chances
Yeah, you
are
can
very
show that through lab experiment.
So in that case,
Yeah.
CSR will be higher than
Yeah.
CSR.
Yeah.
So liquefaction chances will be very.
You will provide the evidence that yes, no liquefaction will occur. These are my parameters, and that what you are simulating in the lab, when you do the model, same thing will happen.
On the side.
Exactly.
So, actually coming to the deterministic seismic hazard you said. So you said that we have to study limit the 200 mile radius.
Yes.
So in that you mentioned that we have to be studying the tectonic, any activity has been occurred.
Yes.
So is it by that you mean like we have to see the any incident wise you mean?
No.
Or like we have to.
Again, I'm like how you do the studies in India, like I'm not that much familiar. Maybe Professor, you have done some seismic in Indian context, so how you do the seismic hazard analysis. But what we do there, we have the experts. They are experts in the seismic determination, like the active faults. Mostly they are geologists. So they know where are the active faults near to my sites. And then for each fault also there is studies. If that fault will break or rupture, what will be the event? So all these are considered during the deterministic analysis. Each one individually we consider and then determine which one will be the maximum and we consider that. You want to say something? Yeah.
if you want to know more about the DSH and the PSH, I have two works published in Natural Hazards and Bulletin of Engineering Geology. There I have discussed about the seismic hazard zonation of Dhanbad city following the DSH and PSH. So you can find those two papers, and those two papers are quite self-explanatory. So how you can go ahead with the seismic hazard analysis, as you sir has discussed in brief, you can get more details, and it's kind of tutorial kind of thing.
No, sir, I was asking, referring to the tectonic activity under the ground. So
Yes.
will that contain that? Or
Yes. Basically, we used to get the tectonic setup from the Geological Survey of India mapping, and in there they have categorized, or they have given all the seismogenic faults for all over India. Now you consider your site, you consider, as said, that 200 miles or 100 miles radius, and you get all the details of the seismic faults, right? And then from various sources you can get the earthquake records, that how many earthquakes of what magnitude, what acceleration has happened in that region for last 100 years. So you get that earthquake details, you get the seismogenic faults, and then based on those records you go ahead with the analysis of, if you are going for DSHA, you can go for simplified analysis, and if you are going for probabilistic, it will be little complex, but it will give better results in terms of your requirement. Sir is saying 10,000 return period years, return period. So if you are going for probabilistic hazard analysis, you will be getting in with more confidence that yes, this is my earthquake, which may hit if I consider 10,000 years. So you can refer to those two papers. That will give you more details about the hazard analysis. Okay, thank you, sir.
Yeah, I think the Geological Survey of India, what Professor is mentioning, same thing also like our USGS, we have their website, and we go to their website and we select the site automatically. All this PSHA hazard analysis will be available. But a lot of time, we for any particular site, we do a site-specific hazard analysis by the experts. That's a must to do that before we do the dynamic model. Because in the dynamic model, we have to consider like at least 3 or 4 sources. And those sources, we have to show that they are close to our site, like within 100 miles or 200 miles area. And we need to know the details of that, because the time history and then the vertical acceleration and horizontal acceleration, all the details will be the input parameter for our dynamic model.
Sir, what about the vibration caused due to blasting on ground, rock blasting?
That I think simplified, there are a lot of simplified model like the mean particle velocity, and those can be determined empirically, we can do that. And also right now they have monitoring instruments, so whenever you do any blasting, we put those instruments and then see how much area it is being affected. And normally when the tailings dam is there, you are doing anything close to the tailings dam, definitely we will have the monitoring station there, because we want to monitor that. If there is any, we see the high peak particle velocity near that tailings, we have to warn them. Yeah, we avoid any blasting activities close to the tailings dam. Yes.
You will need to do the blasting nearer to that tailing dam. Then what is the safe distance?
That's what I'm saying. The safe distance will be like you will monitor it, and then monitor the peak particle velocity, and then see like how much velocity you are getting there. Based on that, you can decide what will be your. There is an empirical formula also that you can do that. But during, like you are saying, like during the construction of the tailings dam, you do the blasting. But that's in the initial stage. That's what you are discussing.
No. My point is during ponding, during dry stacking, also somebody is doing blasting nearer to our operational pond.
Yeah, like you already have a tailings dam. You already have a tailings dam, and if it is very close to, say, your open pit, if it is very close to open pit and open pit you are doing the blasting. So in that case, our recommendation is you should have the monitoring station at various points in the tailings dam, mainly the close to the pit, the point which are very close to the pit. We put the monitoring station there and monitor it. Like during a blasting, we monitor it and then see what is the PPV and you see if it is exceeding. Because if it exceeds, then definitely we will have to do something or we have to be careful of that. Yes, there are guidelines for that.
Jitin, so one of your questions that you considered in India, so we have 4 zones.
Yeah.
Okay. So suppose today what is the zone 1 that after few years it may come under zone 2?
It
That-
can happen.
Yes.
Is it?
That
It
depends
is.
upon your means in that locality. What are the activities going on? What is the mining? Okay.
Okay.
So based on that, our tectonic movement
Movements.
that changes.
Okay.
So
Okay.
that's why sir what showed one figure that PGA that is changing with the time.
PGA, yeah.
So that depends upon our zonation. Okay.
Yeah.
So now one area is coming under zone 1. After 10 years, it may be zone 2 or zone 3.
Is it?
That's why we have to consider higher value.
But I think I have been referring these zones since last 10 years. In last 10 years, they have not changed.
Around that, even if you are in zone 1 and zone 0, you can never say 100% with 100% confidence that an earthquake will not come.
Is it?
Yes.
It is.
Then
it
what is the
is-
use of these zones, sir?
It is just a guideline
Just
for you to moderate your design.
Okay.
Say you are considered 0.36 G for zone 5 and 0.10 G for zone 1, just to check that your dimension should not exceed.
Ah.
Exceed. But you can never say that an earthquake will not come. Sarah said, telling that blind fault.
Yeah,
That
blind
means
fault.
You may have fault, but you have not detected it.
Correct. That can
So,
be.
and these earthquake or seismogenic incidences occur in a geological years. And geological years means 1,000 or 1
Not
million
small.
years.
Not small.
So you don't know. You may
Future.
maybe seeing for last 50 years, but you never know that whether in 10,000 years ago this site was seismogenic or not.
Yes.
And this earthquake,
Yes, sir.
all the knowledge and things I am following it for last 30 years also, but I am not an expert on earthquake.
Right.
But I am following it. I have done some of these deterministic analysis and also the probabilistic analysis. Myself, I have done that. But the thing is, the knowledge level and our interpretations, it's always varying. We are always getting, like, if a big event will occur, that will again change everything. Recently, I think 2 months or 3 months back, there was a big event happened in, I think, the Bangkok or in that area, where this Bangkok, that you saw that whole building collapse like vertical. It's like a playing cars. The whole thing collapsed vertical. I saw that, and the source was 200 miles from there. Because that area was previously considered not that earthquake. So now, that zone, if it is zone 1 or 2, now it will become zone 4. Because the source is unknown. We are saying this is again, it's depending on our model, our knowledge. But still source is unknown. We locate it, but how deep it is occurring and what kind of event is still not known. And all these PGA and things you see, are all experimental model. The PGA is not directly related to a energy. It's a experimental model. We say it's the high, like it's a magnitude is 7, magnitude is 8. If you see their classification, those are experimental classification. How much damage has occurred, then it gives you that number. And based on that number, your PGA is coming. Because your higher magnitude, you go for the higher PGA. So these are all experimental model, and again the knowledge level is still increasing. People are doing still a lot of research. I can give you one example, like in the Los Angeles, in the California, they have a big fault, big active fault which has already been detected. In one of my earthquake class, we were assigned a project to predict it, when that will happen. I took that class in 1992. We predicted it will happen in 2021, I remember. Because we did applying all our theory knowledge, we did the prediction that it will happen in 2021. But it has not yet happened yet. And but a lot of research is still going on, and the people are like nobody can predict it, but the people are trying to see if we can identify little ahead that something is happening. That's why all this monitoring is going on. In my, like when I will show you later on the slide, like there is a INSAT technology which they are monitoring from the satellite, from the space. And major part of that satellite, the cause of the satellite is to detect, if you can detect a little bit ahead of those earthquakes. Because that's, if that earthquake will occur in California, you can't imagine what will be the cause.
And sir, in infrastructure industry, some of the consultants, they recommend to do some test at the site, and they are going with the site specific PGA in their design.
Yeah,
is it correct way of doing that?
Yeah, that's what we are showing. Like you have to do site specific probabilistic seismic hazard analysis. This probabilistic seismic specific analysis is site specific. It's belong to that particular site.
That particular site.
Yes.
And they use PGA derived from that test.
Exactly.
That test.
Yeah.
Because in code there are some PGAs given for through the guidelines that this much G, this much G, and based on that the PGA should be used. But they recommend some test to be performed, and that PGA they use in
Exactly. That's the method.
That's the correct method.
That's the method.
Yeah.
Sir, because of seismic effect, the core water pressure increases.
Yes. That is already been seen in many events. Yeah, that's the thing. And you can see that when we simulate it, I showed you the value is increasing.
And decreasing the effective stress.
Exactly. That's how the cyclic liquefaction is occurring, and we there is a lot of advance in this lab testing in the recent years. So there are very good lab equipment available, like the laboratory I have seen also, they simulate the seismic event in any magnitude and do the lab test.
Because of this, the vector of safety also comes down to.
Yeah, definitely. Once your CSR is increasing, then the factor of safety will be down.
Any more questions?